Thanks, Michele, and I'll take the chance to thank you and the editorial board of Bayesian Analysis for having invited this discussion. And of course, thanking the discussants for their interesting comments. It's been a great experience having what is going on. So, as let's see if this is popping up. Okay. As already Michele said, this is a joint work. This is part of the work I did during the PhD, jointly with Amy and David from the university, and Andrew Olshan from UNC Chapel Hill, who is one of the epidemiology, who is part of the epidemiology group dealing with data from the National Birth Defect Prevention Study. So the main topic of our paper is clustering, which is one of the canonical data analysis goals one can have in statistics. And we take a model-based perspective. So we rely on discrete mixed models rather than methods that, rather than methods that use that are only based on distance. We consider Bayesian perspective in this case. And the nice thing of having a Bayesian perspective is that typically you can incorporate prior information. So in this view, we ask ourselves, what if we have prior information on the clustering itself? And this question actually popped up from our motivating application in epidemiology that deals with birth defects data. And typically, aim of epidemiological data analysis is to try to relate exposure factors to the development risk of disease, and in this case, birth defects. In this context, there's usually prior information available that can come from the biology of the problem or experts' judgment, for example. So motivated from this application, we were trying to develop some methodology that was able to cluster the data using information that we have in the data, but also the external knowledge. So I'm gonna talk a bit about the study from where the data comes from. So to give you an idea of what's the setting we're looking at. The National Birth Defect Prevention Study is a population-based case control study that has been run since 1996 and is still going on, so it's been run for more than 15 years. It monitors 37 major birth defects of unknown etiology. This means that defects, diseases, which we already know the causes, are excluded from the study. And there are many different types of defects, some related to the heart, to the pulmonary traits, or you have something like, I don't know, malformation of the cleft. I mean, you have all these, they're pretty heterogeneous. In that sense. So cases are monitored through surveillance system, while controls are enrolled taking from using hospital records or birth certificates, and usually are healthy, and they are healthy babies. Data is collected via telephonic interviews, and where the mothers are asked so many questions, like what they were eating during pregnancy, what they were doing, all the possible habits that can have some meaning. So when I was introduced to this study, the people working with the data were calling the data set the baby monster. So just to give you an idea that there is a lot of information and this huge data set to deal with. Since we wanted to start from something, we decided to pick a subset of the data. In particular, we focus on congenital heart defects, which are problems that occur in the structure of the heart of the baby. We focus on this particular subset for different reasons. One of these is because of the clinical importance of the problem. Since heart defects are the most frequent class of defect that occurs in newborns, and they have an high impact of pediatric mortality. So these are like the priority when you want to study this disease. While from a statistical perspective, it's challenging to model these defects as most of them, many of them are rare to be studied individually. And what researchers do is to lump together these defects in different groups. But this is, it is hard to group them. It's difficult to determine how to best group these defects. However, there's a leading theory on this that are called mechanistic classifications of the defects. In the sense, this is a classification that relies on the on biological knowledge on how the embryo developed during the pregnancy, rather than anatomic features of the heart. So the long story short is that parts of the heart develop together during pregnancy, and so the idea is that if something goes wrong in that phase, you can have this can lead to one of the defects in this group, for example. So from a mathematical perspective, what you have is a grouping of the data, an initial partition for the data, and in order to find out how to account for this partition, we kind of started from the basics. So we asked ourselves, what is this object we're dealing with? From a mathematical perspective, this is called a set partition. And a set partition is a collection of non-empty disjoint subsets, such that the union of the subsets gives back to the initial partition. And I kind of like the story behind this object, as this goes back to the 15th century in Japan. It seems they were the first coming up, started to be interested to all the possible groupings of objects, because during that time it was a popular game that was played during the tea ceremonies. So during these ceremonies, there were the game master picking 5 sticks of incense and asking the player to smell these sticks and put together the sticks that had the same fragrance. So it was a guessing game, try to pick the ones that are the same. And so they started to come up with these sort of representation here. So where at the top, this is the case of all the 5 sticks are different. Then in the second and third row, 2 of them have the same fragrance, and 3 in the fourth, fifth row, 3 of them, and so on. And eventually, it seems that the game was banned because of gambling. So what was left was just a map. So this is an interesting combinatorial object for which we can describe which I can give some description. For example, we can say what is the total number of partitions, which is given from the bell number. We can say how many partitions of n what's the number of partitions of n into k blocks, so how many of these colored patterns you can have. And we can also describe some properties of the partitions. For example, there's this one that I want to highlight that I call configurations, that is the sequence of block cardinalities, so for the case of the partition with only singletons, you have a sequence of 1. If you have a group of two elements and the singletons, you have a sequence of 2, 1, 1, and so on. This would be helpful to illustrate our proposal later. So this was the mathematical representations that a partition, but a partition is something that we already use a lot in Bayesian mixed models. Typically is the line parameter of the model, and just to remind you, in a Bayesian mixed model, one base assumption is that observations are conditionally independent given the clustering, given the set partition. So one can describe the probability density function of observations as the product of k probability density function, 1 for each cluster. And usually we have, for each cluster, we have a set of unknown parameters we wish to estimate. We also wish to estimate the partition itself. So usually in a Bayesian framework, you assign a prior probability to each element in the set partition space, so that you can have a posterior of this form. In absence of information, one may want to use, one may want to put a uniform prior, and the equivalent for the partition space is 1 over the total number of partitions. However, this is hard to use in practice, and there are other ways to, there are other clever, more clever ways to do it. Are there any questions? I'm rushing a bit.
Not so far, but this gives me the opportunity again to remind everyone that they can ask questions in the Q&A section of the webinar. Thank you.
Great. So, as putting a uniform prior is not so global in practice, I mean, it's harder to use it, hard to do in practice. Usually people rely on, for example, discrete non-parametric priors, which are priors that have discretization almost surely. And I'm talking about, for example, the general class of Gibbs type priors that typically induces a latent partitioning of the data. And sometimes this partitioning can be described in probabilistic terms via the exchangeable partition probability functions. And not always this can be written in a closed form, but there are cases, notable cases such as the deletion process, the fitment process, in which you can come up with an analytical expression of this EPPF. I mean, this is nice in the sense you can induce the partitioning in an indirect way, and you don't have to deal with the probability defined set partition space directly. But the drawback, kind of drawback, is that the prior probability depends on the number of cluster sizes. So what we have so far is that for our prior on this set partition space is that either we can put a uniform distribution, so each of the elements in the set partition space has the very same probabilities, or we can use a deletion process or Pitt-Major process, and this will give the very same probability, prior probability to partitions that have the same configuration. So all the partitions that have, for example, a group of 2 elements and 3 singletons, they have the same probability a priori. So thinking of our motivating applications where we have information, we have one specific partition, maybe is one inside of this group, but we don't want that the other partitions in this group are as likely as the one that we know. So we came up with what we call center partition process to account for the information that we have. Our base idea starts from, our basic idea is to start from a baseline EPPF and penalize it using an exponential term. So we can define our prior for a partition C as proportional to a P naught, a baseline distribution that we indicate with P naught C that we define to be an EPPF on a set partition space. Then we have this exponential penalization that depends on 2 parameters, 2 elements, let's say. A distance between partitions that accounts for our prior guess C naught, and ideally we want this to be a metric on the set partition space. And finally, we have a penalization parameter psi that controls for the amount of centering, the amount of shrinkage that our prior has to C naught. And we have, in this case, 2 extreme situations. For example, if psi is equal to 0, we go back to the EPPF, to the original baseline EPPF. So we don't account for information in C0. While for psi that goes to infinity, our prior collapse towards is a point mass on the partition that we have. So we defined our prior probability as proportional. We can work out an analytic form, starting from defining sets of partitions that have a certain distance and a certain configuration for each possible combination of distance and configuration. And this allows to write this formula in the middle of the slides, which, however, is not analytically tractable. And we can go back to different cases according to choosing different type of G, where G is a function of a configuration. If the G is equal to 1, this represents the case of a uniform EPPF, while we can take a G equal to we can take a G being the proportional piece of the initial process. So, as I said, we have, so in this hour from ratio, we have different elements. So we have an EPPF, we have distance, penalization parameter, and our prior information. So let's say that as an EPPF, we fix the choices among the uniform or the initial process. So I put my jar and go to see and check which are the other elements that we have to choose. First I want to fix distance. And to choose the distance, we rely again on a bit of a theory of the on properties of set partition space. You can endow the space with a partial order, so you can define and come up so that the partition space is a partially ordered set with opposite for short, and this allows us to represent the space using this diagram, which is called Hasse diagram, where usually at the top you have the partitions with a singleton. At the bottom, you may put the partitions where all the objects are clustered together, and you have all the cases in between. So this can this defines the notion of partial order. And to define a distance between partitions, we can start from this Hasse diagram and pick a lattice function, so a function that is defined for each element of the space, so that this function defines which is the weight of the edges that connect each of the partitions. And the distance between the partitions is the minimum, the path that has the minimum weight. So, for example, if I want to want the distance between these two partitions circled in blue, I need to find the path between these two partitions and just take the path that has minimum weight. If I take a trivial lattice function that is, for example, the number of clusters, both these two paths have the same weight. But if I take something else, such as the entropy, this would be the path that has a minimum weight. So different choices of functions leads to different distances and different concept of neighborhood on this space. We favored in our paper the variation of information, which is a resulting distance from choosing this entropy function of the space. But other distances can be defined in a similar way. I mean, we are okay as far as this is a metric on this space. So now we have the EPPF and the distances, and we want to see what happens for different C naughts. So what happens if C naught is in what happens to our prior, depending on the position of C naught inside the space for different values of psi. So in these plots, I'm showing the cumulative density function of all the possible partitions of 5 elements. And the area between the lines represents the probability of the partitions. These probability are shown for different values of psi, and the area that is colored is in place of the C naught or the partition that we have as a prior information. In this case, in this first plot on the left, we have that C naught is a partition where all the elements, all the objects are grouped together. So for psi equal to 0, in this case, all the partitions have the same probability as the EPPF is uniform, but as psi increases, there are some of these, I mean, there's more prior mass on C0, while partitions that are close to C0 are more likely than one that are distance according to the definition of distance that we chose. Similar story goes if we pick C0 in another part of the space. And but the partitions, I mean, the partitions that are closer to C0 are different, and the probability that they can have for the very same value of psi can be different. So this tells us that value of psi can have a different effect on the prior, depending on where C0 is in the space. And this is even more evident when we take the Dirichlet process as a EPPF. So even in these plots, I've picked this very same C0 partitions, and for example, when we consider a Dirichlet process with alpha equal to 1, the partition with all observations altogether is the one most likely a priori. So if we put more weight on this partition, the a priori probability for this partition becomes like overwhelming with respect to the others. While the story is different if we take, for example, this C0 partition where there are two clusters with the same size and a small one. So it takes a larger value of psi to inflate the prior probability for this partition, the one that are close. Are there questions?
Yes, there is indeed a question. Duke Chowdhury is asking if the method is sensitive to the choice of nu.
Yes, because I mean, yes and no. I would say yes, because I mean you define a different concept of distances, so the neighborhood of what you define to be closer to your C0 depends on the choice of distance. However, many, I mean, depends. I mean, some distances can give similar neighborhoods. So why some others can be really different. Yeah. I guess
Perfect. We can, you can, I mean, we don't have other questions, so.
Okay, I'll go on. Okay, so let's assume that, okay, we're okay with the distance we chose, we're okay with the EPPFs, and since, from this plot, we get the feeling that psi depends on C0, so it depends on the prior partition that you have. So it's hard to pick a general, so it's hard to pick a value of psi, general value of psi. So to choose psi, we decided to choose it in a sort of indirect way. In a sense, we, instead of looking directly at psi, we looked at the distribution of distances from C0. So given this random variable, so this random variable, we can define the probability distribution and look at the cumulative probability function. So that given this cumulative probability function, we can take an ideal distance, let's say, and a probability Q, and choose psi such that our CP process places probability of Q, let's say 0.8, to partitions that are within a distant delta star, that in the case is equal to 1. So instead of choosing psi directly, we choose this pair of parameters, a distance and a probability, and get psi such that that's this meaning. However, the hard part is that we need to somehow get an estimate of this cumulative probability function. And to do so, we rely on a computationally expensive algorithm that uses that samples uniform mirror partition space, so that we can get a Monte Carlo estimate of the CDF. We pair this uniform sampling with a deterministic local search, in the sense that we locate our CNOT partition, let's say, in the Hasse, where the CNOT partition is in the Hasse diagram, and following the path even from the Hasse diagram, you can explore the partitions that are nearby, and we do it in the neighborhood of CNOT to be sure to get at least some partitions that are close to the one of interest. And so now we have all the ingredients to build out we're the ingredients to build our prior. So I'll go back to our application for defects. And we have, we came up with, I didn't talk so far how we modeled this birth defect. So we have 26 Earth defects indexed by I. For each of these defects, we have an I observations, and this number of observation per defect is pretty different across the defects, so there's a lot of heterogeneity, let's say. And then we have a response variable Yij that indicates if observation J has birth defect I, and if it is a control. So we have, putting all the cases together, we are about 4,000 cases and 8,000 controls. And then we have, we assume that we have a set, we have a set of covariates. There are 90 risk factors that we pick among all the inside of this big data set. And what we are basically doing is sort of grouped logistic regression. So as usual with logistic regression, where we have a random intercept for each defect, and we put, we cluster together the effect of the covariates, so that defects in the same group will have the same relevant risk factors. And to do so, we put our prior on the clustering. As a CNOT, we have a grouping. As a CNOT, we use grouping that is given in a paper from Otto, and they consider 6 groups for our 26 defects. While we use as baseline a EPPF the Dirichlet process, and we will fix the parameter, the concentration parameter equal to 1. So from the prior calibration, we get, we choose a value of psi equal to 40, which translates in 90% of the partition. We have probability that 90% of the partitions are within a distance of equal to 0.8. However, we also decided to look at what happens for larger value of psi. So we performed the analysis starting from psi equal to 0, which means that we are using just the Dirichlet process. So we are not using any information comes from CNOT, and choose other values of psi, so that we are more and more considering the CNOT partitions until to psi equal to infinity, let's say, which correspond to just run separate logistic regressions for each group. We estimate the parameters via MCMC. Just give, we can get a deep sampling in the setting if we put perform data augmentations of polygamma on the variables, and just mention that we use marginal sample, the classic, marginal samplers that are used for random partitions to allocate objects to the partition. And here are the first, some of the results for our application. So these plots are kind of the standard pairwise allocation matrices where with modifications where the these colored dots are in place of the prior grouping that we have with these defects. So same color means the same a priori group. In this first allocation matrix, in this first plot, this first plot comes from a run where we don't use the prior information. So this is the clustering from a deletion process that just gives a one big group and a small one. So why, if we start to include to use some of the information from our CNOT, we get something that some clusters that resemble our priori information. For example, we have all the birth defects in the pink group that are clustered together, along with one from the pink group, while similar stories for the other two clusters. And the larger value of psi, we put more strength towards partitions in the smaller level of CNOT, so that we can go to cases, for example, like in the last plot for psi 120, where all the groups are kind of recovered. I mean, they're just grouped together in smaller groups. So for six group, we get like 3. And finally, we looked also what happens. We also looked at the results of our the estimates of the regression coefficients, and we decided to look at them across. To look how this regression coefficient changes for different value of psi. So in these plots, I chose 4 different birth defects, some of the exposure factors, and cells in the heat map are colored according to the value of the estimated coefficients, with dots indicating whether that coefficient is significant. So red is bad, is negative for significant is bad for is bad, and green is positive. So anything is red will increase your probability to have one of these defects, while the green one would prevent that. And looking at the result of this analysis, we actually found out some of the risk factors that are significant are kind of already known. So this known that if some relative has already had some birth defect, this increases the probability that the baby can have a birth defect. This is true across most of birth defects. Similar goes for the type 1 and type 2 diabetes, and also now same goes for factors that have a positive impact, such as nausea and taking folic acid supplement, which is good for the baby's health. While it is interesting seeing what happens in the two extremes. So when you just rely on the deletion process or just on the given groups, and maybe the most relevant cases is the one for the ABSD, which is one defect that is meant to be in its own group. So that is in the prior partition that we have. So if it's analyzed alone, we don't get any significant exposures. Just basically because we don't have enough information for just this type of defect. So it's putting together with all the defects benefit analysis, so we can get information on what are the factors for this. And while this is dangerous also to use only the deletion process, because you can get weird odd results, such, for example, this positive effect of drinking alcohol, which is something you don't want to see in statistical analysis. And I think I'll stop here, and I apologize because there's some noise on my side. So I hope you don't hear that. So.
No problem. Thank you. There was some background noise, but I understood that there was not much you could do.
And I'm throwing out the leaves. That's
yeah, no, I have the same problem sometimes here when the gardener blows leaves. Okay, thank you very much. So we actually have a question, and probably I can expand this question also to other to the other authors. And again, I want to thank Sally for her presentation, Amy, Herring, David Dahl, and Andy Olshan are the other authors of the article. So there is a question about the feasibility of estimating psi. Is there information in the data to do so?
This is a great question. Do you? Sorry, can I ping it to my co-author since it's too noisy?
I mean, I think there's. I think there's definitely information in the data. Just like you could imagine choosing a pretty flat prior for clustering, and then trying to estimate what the clustering is. In that case, and in here we're basically shrinking towards some prior guess on clustering, and the degree to which the data are consistent with that clustering, that's determined by psi largely. And so how close the data are to that. And so we have information in the data, but it's more of a technical problem because it's not so straightforward to just put a prior on psi and then run MCMC, because it occurs in the kind of normalizing constant. And David Dahl in one of the discussions mentioned some good ideas for getting around that hurdle, but it's more of a computational problem than. But I think there is definitely information in it. That said, I wouldn't want to choose a flat prior for psi, like that was very diffuse, and then maybe then it would just like kind of go back to what being just completely data based, which might be unreliable, I think, because we do want to include this prior information. So.
Perfect, thank you. So we will leave other questions to the end. As David has mentioned, David Dahl and Thomas Jensen, Richard Ward has written a discussion. Another discussion was Adam Smith. I also want to make a shout out to the many contributed discussions that we had by Isadora Antoniano Villalobos, Cristiano Villas, Sarah Wade, Alejandra Avalos Pacheco, Roberta De Vito, Sarah Wade, again, Tommaso Rigon, Emanuele Aliberti, Massimiliano Russo, Bruno Scarpa, Laura D'Angelo, Antonio Canale, Christian Henning, and Alessandro Casa, Michael Fopp, Thomas Brendan Murphy. One characteristic features of the discussion papers in Bayesian analysis is the ability to leave the possibility to everybody to contribute discussion, and this has been a lively discussion indeed. So I will start with David Dahl, Thomas Jensen, and Richard Ward for the discussion.
All right, can everybody hear me okay?
Perfect.
Great. Well, thank you, Sally, for a fascinating paper, and thank you, Amy and Andrew and David, co-authors. This is a really interesting paper, and I think it opens up a really interesting area of research. I want to acknowledge my co-authors, Richard Ward, professor here at BYU, and Tom Jensen, a master's student at BYU who's finishing up. So I first became aware of this paper in 2019. There's an archive paper, but also Adam Smith, who's the second discussant here, discussed after us. He came to BYU and presented his work. And I think both of these papers deserve credit for blazing the trail for a new area of research. You know, we, as Bayesians, want to be able to model our parameters of interest. We might have a best guess as to the value of the parameter, and we want to center our prior distribution on that best guess. But previous to these two papers, we didn't have a way to go about doing that in the context of partition distributions. So I think that's fascinating. Beyond just the credit they get for coming up with a really interesting area of research, I think there are particular strengths of the formulation associated with the CP process that we heard about today. One is that the probability mass function is just super simple, which I think is an attractive feature. It can accommodate any baseline EPPF, which affords a lot of flexibility, and also can accommodate any distance metric. The default that they use in the paper is the variation of information distance, but you could use any partition distance metric. It's also very easy to see how the penalization parameter psi influences the distribution to penalize departures from the center partition C0. And we think that's great. I think one of the concerns, and I think David Dunson alluded to it in his answer to a question, is that the normalizing constant is undefined, or that is, we have the probability mass defined only up to the normalizing constant, and that's going to make it so that we need to find some way to fix the value of the psi parameter. And Sally presented in the paper, Paganin et al., a really creative prior calibration algorithm that works really well for their data analysis. This is figure 7 from their paper, and they illustrate this idea. This is where we had n equals 26, but in the application we saw or n equals 12, excuse me. But in the application we saw n equals 26 for the birth defects. The center partition C0 is the configuration where we had 4 clusters of equal size, 3 in each cluster. And we think that the prior calibration is very creative, but we wonder, what about just simply sampling from the CP process prior using Markov chain Monte Carlo? Certainly you already have a means to do Markov chain Monte Carlo in the context of the CP process to do posterior inference, and just go ahead and turn off the likelihood, and now you're sampling from the CP process prior. And we think then you could follow the same framework to pick a value of psi that leads to the characteristics you want in terms of the distance and the proportion of partitions that are within that distance from the center partition. We went ahead and did that for n equals 96. We had a total of 8 clusters with 32 items. I'm sorry, 8 clusters with 12 items in each cluster. And let's see, so on the left-hand side, we have the uniform EPPF, and on the right-hand side, we have the Dirichlet process with mass parameter 1. When the penalization parameter psi is equal to 0, we recover the baseline EPPF. And as we increase the penalization parameter, we get distances from the center C0 that are closer and closer. And that's, we think, very nice. But as we study this figure a little bit more carefully, and also we go back to even figure 7 from the original Paganin et al. Paper, we see a behavior in these CDFs that isn't quite what we would have expected. And that's because I guess we were expecting to see something more like this. Think about a Gaussian distribution, and we have a parameter then on the real line, and we want to center our guess based on our prior knowledge. Suppose that center is going to be 0, and depending on your penalization parameter, which is related to the variance, we have lines, CDFs, coming out from the origin with different slopes based on the value of the psi. And that's kind of what we would have expected if the distribution was centered about 0. Well, or in the context of partitions, we would have expected that the CDFs would have been coming out from 0, but instead we see that there's like a threshold where we need to get to a certain distance before we start accruing cumulative probability. And we see that here, but we also can see it here in these plots too, where it doesn't come out from the origin like I might have expected. That got us thinking a little bit more, and we realized that perhaps the term center in this context is a bit of a misnomer, that perhaps really the C0 is not the center of the partition distribution. Let's think about what the mean partition would be. The Bayesian analog of the Hasse mean for a partition distribution is the partition C hat, which minimizes the expected loss for some partition distance metric, such as a variation of information. And so the idea is that looking at these stack plots that Sally had in her presentation, when the center is, say, here or here, and the psi value is large, we certainly have that the mean partition, as defined by the minimizer of the expected loss, does correspond to C0. But for psi being smaller or medium size, we have the mean partition not being equal to the center partition. So maybe the term center is a bit of a misnomer. We're not really centering the distribution about the best guess. Rather, what we do is we have a best guess in C0, and we also have a baseline EPPF, and those two things are competing for each other to define the partition distribution. And we think that that illustrates then the next point, and that is that there could be maybe potentially an incompatibility between the center C0 and maybe the baseline EPPF. On the right-hand side, we've got the Dircer process with mass parameter 1, and the rich get richer property that we know about in the DP process, we think is not compatible with the center with 8 clusters with 12 items in each cluster. And therefore, we're seeing kind of this strange non-smooth behavior in these CDF plots, at least on the right-hand side. On the left-hand side, we'd say that the C0 is indeed compatible with the uniform EPPF, and we get very nice smooth behavior in that context. So fixing the penalization parameter psi, we think is a necessary thing to do in the context of this formulation. But it's not just that we can't make posterior inference on psi, we also must fix the other hyperparameters associated with the EPPF. So we're talking about like the Pittman-Yor EPPF, where we've got a concentration parameter and a discount parameter. The normalizing constant will depend on not only that psi value, but will also depend on the hyperparameters of the baseline EPPF. And as such, then, we also can't make inference on these hyperparameters, which we typically like to do in Bayesian modeling. I think the last point, I'm running out of time, is just to point out that the CP process is very flexible in the choice of the partition metric that we're using to penalize departures from the centering partition. But we have to be a little bit careful with the VI, at least, which is the default in this CP process paper. And that is that we may be required to go from a current state, as we go from a current state to maybe see the high probability state in the center, we may be required to go through a state of low probability because the one at a time Gibbs updates that we typically use in the context of these partition models has it such that the VI really penalizes these singleton clusters. And so it's then hard to move from a current state to a high probability state because of the particular choice of the distance metric VI. We note that this problem does not occur for, say, binder loss. And so maybe in an application, you might consider not only using VI, but you might consider other loss functions, such as the binder loss. So with that, we applaud the work of Sally and her co-authors. This is, I think, really interesting work. This is something that's caught our attention, and we're working on similar areas of research. And judging by the number of contributed discussions as well, this is certainly a path-breaking paper. Thank you very much.
Thank you, David, and thank you again to Richard and Thomas Jensen, to Richard Ward and Thomas Jensen for contributing to this discussion. The second discussant is Adam Smith, and I'll leave him the word.
All right. Thanks to Sally and co-authors for writing a super interesting paper. Thanks to Michele for the invitation to join and be part of this discussion. Happy to be here. So I'm actually a marketing professor at the UCL School of Management. My research area is kind of in the space of Bayesian econometrics. I've kind of worked on random partition models in the context of consumer demand estimation. And so I'll probably have a slightly more kind of applied focus to this, but I think at the same time, I'll kind of echo a lot of the comments that David already alluded to. So to kind of open things up at a very high level, how I think about this paper and this kind of stream of work is that when we think about the kind of the very broad spectrum of applied Bayesian work, I mean, location scale type models show up everywhere. So this kind of canonical problem of prior elicitation, the Gaussian distribution is one of the favorites, in part because it's super simple. There's a mean, there's a variance. The mean tells us kind of the center of what we believe. The variance tells us how strongly we have that belief. And so I think it's just a really nice, these location scale models are a nice way of kind of encoding the information that we already have. and kind of bringing that to bear on an analysis. And then all the way from prior elicitation to actual sampling strategies. So think about that kind of MCMC in a non-conjugate world. I have to maybe do Metropolis Hastings. I need a way of generating proposal values to compute this kind of likelihood posterior ratio. And so, how do we? What's one of the favorite kind of Metropolis Hastings algorithms? It's random walk Metropolis Hastings, right? So I'm using this location scalar, just a Gaussian distribution, to propose new values that are kind of close to where I was before. So I think these location scale models show up everywhere in applied work. And so I think a really interesting question is what happens, the way that the models that we're kind of most familiar with, that we use a lot, are kind of models where the parameters are well behaved. They live in the Euclidean, or they live in the real line. We have a nice Euclidean measure of distance. But what happens when we move into more complicated parameter space, more complicated models? And I think that's where this paper comes in. And so the idea is to think about how we can kind of write down a coherent kind of prior model for a clustering parameter, partition parameter, which is, super high dimensional, very discrete, complicated, right? As Sally kind of alluded to, I think a lot of people that work on clustering problems kind of have priors, and they kind of know maybe a rough sense of what the grouping structure should be. So wouldn't it be really nice if we could bring that information to bear on the analysis? And so in my view, this is kind of like a textbook application of location scale type models, but it turns out to be really hard to kind of work out the mechanics of how to build that model in a coherent way. What this paper does is they provide a mechanism for doing that. So they want to build this a probability model for a partition parameter that depends on this pre-specified clustering. So the typical approach, there has been in the past 10, 15 or so years, there's been kind of a stream of work that has emerged to think about how we can incorporate other information, not necessarily kind of prior guesses on the clustering itself, but just other information in these models. And the typical approach is to build up an entirely new kind of EPPF. And that's really hard. And so I think what's kind of a cool and clever approach in this paper is to say, let's just take an existing EPPF, right? To think about kind of the probability model for partitions that's, say, induced by the Dirichlet process, something that we're all kind of familiar with. Let's just add this penalty term that is going to penalize being farther away from that initial guess, C0. So I think that's a super cool idea, and as David mentioned, it's I think very appealing. And we can kind of see how the flavor of a location scale model shows up, right? So as we think about these limiting cases for the psi parameter, as psi gets super large, then all the probability mass is really going to concentrate on that initial partitions C0. So in the next few minutes, what I'd like to do is just kind of talk about some practical considerations for thinking about building models like these, using models like these. And so the first two are kind of around elicitation, which I think is, if we're going to take this as a kind of a legitimate model for what we believe, we should think about that kind of prior elicitation process carefully. I'll then talk about kind of sampling strategies, things that David already mentioned, and then wrap up. So I think that this centered partitioning model is super attractive for lots of reasons. Unfortunately, I think that prior elicitation is still pretty hard. And so one of the reasons is that think about this kind of hypothetical scenario where suppose that the space of partitions is small enough and we can actually enumerate all of them and kind of rank order our beliefs. And so suppose we do that, and then we say, okay, is it actually kind of likely that that these like top ranked partitions based on our beliefs are actually close to each other in the sense of some information-based distance metric like the VI that's used in this paper? So maybe in other words, suppose we just fit two models, right? Like super simple. There's no kind of formal modeling of the partition. We're just going to fit two models that condition on a partition. The first model conditions on what we believe to be our best guess, C0. And then we'll also come up with another kind of second best guess. And so the question is, does C0 prime, this kind of second best guess, does that necessarily have high probability under this kind of CP process? And I think not. I mean, not necessarily, right? It may be. But I think just by virtue of the way that we think about kind of grouping things and the discreteness and kind of complexity of that space, I think that when we start to move around small neighborhoods of that center partition, we actually could be thinking about kind of somewhat insensible guesses for what that partition is. And so even if we get kind of the center thing right, maybe we're actually still spreading prior mass around the wrong kind of regions, global regions of this complicated partition space. And so what can we do about this? I don't think that all is not lost. I think there's still ways to kind of use this machinery to kind of truly incorporate prior beliefs. And so one way to do this is to, instead of just having kind of one fixed centering partition, maybe we could input a few of them and then have this kind of point mass mixture prior that says that the centering partition is some kind of weighted average of these kind of discrete points in the partition space. I think the nice thing is that that would at least help us to kind of distribute this probability mass in the right regions a priori. Another approach is maybe thinking about trying to build in some kind of pairwise information into this model. So I think David Dahl has done some work on this in the 2017 JASO paper. I think this is just I think a lot of these, the centering, the CP model kind of collapses as a special case of this more general pairwise information approach. And so maybe if we actually have information about that could inform us about the likelihood of two items co-clustering, maybe that would be nice if we could actually build that into the model as well. Okay, so the first point is around kind of elicitation of the centering cluster. The second point is around the treatment of psi. I think this has come up in other questions and certainly David's discussion, so I won't spend too much time on this. The one thing that I did want to mention is that, as someone that's spent some time working on location scale models in partition spaces, I'm very sympathetic to the challenge of thinking about these kind of scale or variance parameters. And so think about a situation where, I have one analysis, in this paper, they say, and I really love the fact that it's kind of grounded in this really nice substantive application, but, they have one data set and the number of items is 26 and so they kind of figure out a way to choose prior the psi parameter conditional on n being 26. But generally, if we're going to think about applying this to different scenarios, we'd like to have like a foolproof approach to thinking about kind of choosing psi. And the problem that we have is that psi and the role of psi depends on the size of that space, right? So if I fix psi to be 1, then in a world where in a problem where I'm only clustering 5 things, that's going to imply a very different kind of strength of belief than it would where I had 50 things to cluster, and then all of a sudden the partitioning space kind of blows up, and it's super, super large, right? So it's actually really hard to in a coherent way think about choosing psi. And I think the authors do a really nice job of proposing a method to do that. And what they say is, let's repose this problem. And instead of choosing psi or eliciting psi directly, let's instead choose this pair, Q and delta star, such that the CP process is going to place probability of at least Q on partitions within some distance from that centering partition. And the key here is that they're using these information-based distance metrics, like the VI metric, which is actually n invariant. So in principle, if I choose Q and delta star, that is invariant to the size of my clustering problem, which is fantastic, right? The problem, as I think David alluded to, is that in practice, there's some kind of heavy computation that has to be done on the front end just to figure out what is sensible. And so as David kind of mentioned, and I know it's obviously the mechanics are challenging, it would just be nice to think about how we could kind of maybe also treat psi as a model parameter. The last thing, which I think, again, David already mentioned, so I'll just echo that statement. So their posterior sampling strategy relies on these kind of canonical Neal 2000 algorithms for hearsay process mixtures. The idea is to iteratively draw from these full conditional distributions. So this is kind of a classic kind of local move sampler. So maybe we would be concerned that the local moves are not going to really allow us to sufficiently traverse such a complicated posterior. I think that's something you can always say in these models, or this kind of class of models. I think why it's important here is because we're actually writing down a prior that is more dogmatic, right? So we know that the posterior will become more concentrated, right? Just by virtue of writing down a slightly more dogmatic prior. But what we don't want is that the sampler to just mechanically get stuck in these regions of high prior probability. And so, again, as someone that has kind of worked in this with this class of models, I'd love to kind of get your thoughts on how we should start to assess mixing in even an informal sense. That's when I was working on my papers in this area. That's something I really struggled with, and I'd love to learn from you guys. So just to kind of wrap things up again, I think this is a really cool paper. I think a few kind of open-ended questions to close with. So one, I'd love to know more about kind of what you think, which part of this analysis, your empirical analysis, really stands to gain the most by actually modeling uncertainty in this clustering. Do you think, if you just conditioned, if you really have strong beliefs and you just conditioned on that one clustering, how much better or worse would you do? Thinking more also kind of at the back end about model selection, what summary statistics in the posterior can we go after to actually learn about how accurate my beliefs are? Large N problems, I think, are something we'd all like to work on. Certainly in the class of problems that I do, I think that I'd love to be able to estimate a partitioning model that had 100,000 items. But again, thanks so much for writing a super interesting paper. It's great to see these methodological developments come out of a cool substantive question. It's a great way of using these models to actually direct shrinkage in Bayesian models, and I'm looking forward to seeing where this goes in the future. So thanks again.
Thank you very much, Adam. So the authors have prepared the rejoinder, and I'm told that both Sally and David will take on the challenge to answer or respond to these queries.
Yeah.
Sally's presenting something. I wasn't presenting anything.
Yeah, I have some slides, but I think you may have comments.
With BS answers, but
okay. So I go on first and let you wait. The screen. Okay, so first of all, thanks David and the authors and David Dahl and the other and Adam for the presentation and their points. It's very interesting to go over that. And in this rejoinder answer, I'll try to go over your concerns. And I try to group the comments a bit together according to what I felt was like topic related. So I'll start from remarks from Dower and Jensen about the CPU process per se, starting from the name, since we came up with, since we call it centering partition process, and as Dal shows, this is C0 is not always the center of the CPU process. So of course, to define the center of a distribution over the self-partition space, we need the definition of center, and so this is dependent on that definitions. However, we actually realize that C0 is the center of the CPU process when the EPPF is uniform under the loss that picked. That's probably where the name came to our minds. Looking back to this, however, we agree with the interpretation of CPU process as a baseline partition distribution that shrunk the probability mass towards C0. Another comment is about the problem of congruity between C0 and the EPPF. As we saw that, it can lead to no smooth behavior of the prior, which actually thinking about that, conceptually doesn't seem a concern, since it's, we have those two things competing, which is what it is, but we agree that there can be an issue when something from the prior to posterior, and it's good to choose them carefully. And I think that
I might add that just real quick that I mean, I thought it was a great point that David made, this kind of disconnect. And so, one alternative would be to think about, before we start doing this, how consistent or congruent the baseline is to our prior guess. And if we have a sharp conflict there, maybe we should just be using the uniform as a default. And maybe we shouldn't be pulling it in some strange direction. Like if we look at some basic properties of the Dirichlet process and they're inconsistent with our prior knowledge, then maybe we should not be using the DP as the baseline. And so then we can actually be designing partly the baseline, choosing the baseline as well, but a bit based on CNOD and other prior knowledge we have.
So another theme that has been raised from Adam and that top up also some of the contributor discussions is about the meaning of CNOT with respect to domain knowledge. So a question paraphrasing what Adam said, does having this information about CNOT necessarily translate on putting a strong prior on clusters that are within a small neighborhood of these partitions? And this somehow shed light on the implicit assumption that we are making while presenting our skill process. So yes, we are assuming that we want to put prior in a neighborhood, strong prior in a neighborhood of CNOT, and we assume that the probability mass decay exponentially as the distance grows. So we actually, this is a strong prior that we think can be good in cases that are similar to ours, where there is a leading theory and we really wish to interpret the result so on according to the leading theory. However, we agree that these assumptions are not general. They do not hold in general, and as the domain knowledge can suggest other type of prior information, and we may want to apply different clustering concepts to the same data depending on what's the aim of our analysis. This sentence came up by the discussion from Henning that I really like it. However, of course, our formulation is not cannot address all the possible cases, but some examples can be still, some of these cases can be still addressed in our framework, and examples are given were given in some of the contributor discussion as well. And so were different people wondering what if, for example, we have more than one partition, as Adam mentions. This partition can be, for example, alternative to the one that we have, or it can be really, really different so far in the space, or may even they may take a big portion of the space when, for example, when you have partial information about the clustering. And one idea is to use two-stage prior, as Adam suggested, and while another potential idea is to account for this for more than one prior guess, considering the sum of distance. And this was up in the discussion from Rigon et al. And Hasse et al. And from comments in the contributor discussion from Rigon co-authors, it seems that you can tie these two representations together, interpreting that in a generalized Bayes sense. So hopefully we will go to read these discussions. Another alternative was, another interesting point was about whether if we want to, was more regarding the aim of the analysis. So we are okay that we have these CNOT partitions, but we want maybe to favor partition, the partition in a neighborhood of CNOT that is more parsimonious, so that has less clusters. And this is for using Tangelo and Canale, and they consider using different penalization. So we're happy to see these extensions, so we actually can put them together in a more general form for our penalizations that can explicitly account for some characteristics of the clustering. An alternative could be like, if we don't want to have this strong prior and we don't want to really put a strong weight in this neighborhood of CNOT, we can think about CNOT as covariate, as was suggested from Antoniano Villalobos et al., so that it can be used to tools that are already developed in the literature, like dependent initial process or weighted normalized random measures, where the allocation to partition is dependent on information on C0, but it's not necessarily that the partitions close to C0 are more likely to occur. So another point that has been raised is about the computational challenges that we have in our proposal, especially the prior calibration. As we discussed in the slide, we have this prior calibration procedure to pick a value of psi. Adam mentioned that we can, for example, choose a grid of psi and integrate out them from the posterior, doing the posterior sampling. And this is in line, kind of in line what we recommend. I mean, what we did in our application, that we checked for different value of psi what happens. However, we may argue that one may still need a sort of calibration procedure to pick this discrete values that are plausible. Alternatively, David Dahl and co-authors suggest to use the algorithm for posterior sampling to sample from the prior, and actually show that this is possible, and that this is more scalable with them. And we have to admit that we went down this path while writing the paper, and we actually have had some problems because sometimes we found that sampling from the prior was not. So it's the right word to see that not robust in some sense. So we have cases where maybe we observe the sample being degenerate towards the C0 partition, and this motivated us to look into something different that was independent from how we sampled from the prior. And however, this is indeed, I mean, this is really a good alternative, but I would put it conditionally if we improve the sampling algorithms. And on this topic, I mean, on this point, we have also received from David and Adam some nice suggestions. So as I mentioned, we built on the standard 100 times samplers for random partition from MIL 2000. So we're not immune from limitations of the type of samplers, and so we thanks for the suggestions that were given, and of course using split and merge moves or sort of particle Gibbs algorithm should improve how we explore the subpartition space in the posterior and also in the prior sampling. And in particular, also we thank Adam for pointing out what they did in their just a paper of using Metropolis as a move space on the prior developers, since it seems that we can do something similar with our prior. Also, Dahl, Warren Jensen point out about the possibility of inputting to local modes because of variation information. I have to say that we did not observe that in practice, but we agree that this could be a concern, and totally agree that binder loss could be a robust alternative. We actually chose the VI thinking of the prior, of how we can describe it. It was in line with our intuition of a partition neighborhood, but it's not where we are tied with that. And finally, last set of comments are regarding the more about that analysis. So we are super happy that many discussions highlight that the different domains of applications, in particular, Savolos, Pacheco, De Vito, Wade, or illustrated through deeply illustrate application in clinical trials and nutrition epidemiology, and why we think how we can apply more our methodology to data analysis. There are questions that came from Smith on, for example, how to perform the assessment or how to select models. And on this, I just point out that, for example, about clustering, you can summarize uncertainty, for example, using methodology described in a recent paper from Wade and Garavani, in constructing this sort of credible pose and characterizing uncertainty on the clusters. Well, about model assessment, I don't have much to add, apart from using standard tools. Bayesian model assessment can rely on posterior predictive checks or posterior predictive values, better, in my opinion, if calibrated. Finally, on how to scale this for large N, I think that from one side, computational issues, some of the suggestions we received should be helpful in addressing some of the computational issues. However, practical way to do so is to rely on more dogmatic value assumptions so that the partitioning problems lives in a lower dimensional space. This is actually seems reasonable. As in practice, it may be hard to have substantial prior information when there are many nodes as such. That's it. I don't know if Amy, David, do you want to add something?
No, I mean, I think you did a great job.
Thanks.
I mean, I think in some of these large N cases, you do have prior information. I mean, we're working on things like that right now with Tommaso Rigon and ecology applications where you have like just tons and tons and tons of different species. You maybe have hundreds of thousands of different species, but there's an existing phylogenetic tree. And so you have a lot of prior information, and it becomes, you just need to figure out ways to, design priors and algorithms that can avoid running MCMC over the partition space when you're in that high dimension, I think.
I guess another thing that in terms of the application, things that we're thinking about, there are hierarchical classifications available of the birth defects. So Adam had mentioned something along those lines, and you quickly run into sample size issues. Even with the breakdown we use, there's a group with only 4 defects, but that is something that's interesting to consider. And the other thing, when I was talking with Angela Lin, who's a co-author on these original classification papers, is that they struggled more with some of those groupings than others. And so the uncertainty around some of the groups in CNOT is greater for certain groups than for other groups. And so that would be something really interesting for us to be able to take into account. And I guess the last thing is that that swept under the rug a little bit is that the decisions they made about how to code these defects are incredibly complex. And so some defects are actually multifactorial and they involve 4 individual defects. In other cases, if you had 2 defects, they chose to code things separately. And this was for clinical reasons, but that is also something interesting that sort of breaks some of our assumptions that we made in the modeling, but would be something that would be cool to take into account in the future. So people have ideas, the data have really interesting features to take into account.